Hi there and welcome for this video on Senior Physics on Light and Waves. In this video we're going to explore wave interference patterns. Now, wave interference patterns were first generated by Thomas Young in 1803. What he noticed was that if he took two point sources which are classified as coherent, i.e. they are in phase, as a result when one dips in, the other dips in at the same speed and the same amplitude, the result is it will generate the same sort of wavefronts. These wavefronts will interact in such a way that they will produce areas of constructive and destructive superpositioning, the production of antinodes and nodes. So let's have a look at one of the pictures that he generated. Now this is a classic picture of his wave model pattern. Now the best way I find to look at this is to actually look at it as if you're squinting. And what you'll see is two areas. The areas are areas of banding where you get black and white, black and white, black and white, and areas of grey. Those areas of grey are quite small, and they're basically, there is no clear distinction between any of the bands. Now, they are all generated by 2 point sources. As you can see, they're labelled there with the arrows. Now, the areas of banding of black and white, black and white, black and white are our antinodes. These are the areas where we're going to get crest meeting crest and trough meeting trough from the 2 point sources. They're going to interact in such a way that they are going to add to the amplitude, so they're really, really big. So we get clearly defined amplitudes which are generated. In the grey areas, these grey areas are called our nodes, or our destructive lines of superpositioning. Now this is because we're getting a crest meeting a trough. Because these point sources are coherent, the amplitudes are the same. So I get a positive crest with a negative trough. They cancel out, so there is an area of flat calm. Now these will only be on specific points, and as a result what will happen is anywhere between these points we will go to an area of maximum amplitude and then back down to an area of diminished amplitude or flat calm, depending on whether the waves are coherent or not. So let's explore how these come about. So here what I've got is a diagram basically showing that same picture. I've got 2 point sources, S1 and S2, which are coherent point sources, so they're basically going at the same time. All the wavefronts are in phase, and they're the same wavelength, same frequency. Now you'll notice that right down the middle there, where the two circles, the two ripples, or the two wavefronts, or wavefront patterns interact, we get these crossings. These crossings are going to be areas where I'm going to get peak meets peak, and also trough meets trough. And we can get a specific line, and this is denoted by this white hatched line. This is the first antinodal point. It's the point where the waves are going to cross over to make high amplitudes. Now there are others further away from this central point. You can see there's 2 points here. Again, these are where the wavefronts actually cross. And there's another 2 here. And this can go on depending how far we're going to take out those ripples. As well as that, as well as the wavefronts, now these orange lines for wavefronts, I'm going to call crests. We also have troughs, which is shown by the hatched purple lines. Now you will notice where these lines, where the single line through the center goes, you can also see it passes where the 2 crests cross over. Now I've only drawn 2 crests in there, one from S1 and S2, simply to show what's going on. Otherwise it gets very, very confusing and a bit messy. But what I'd like you to understand is that on that first line that I generated, there is a crossover between the 2 crests. So this basically showing, these lines of antinodes are showing that we've got amplitudes, high amplitudes of crest meeting crest and trough meeting trough. Now you will also notice that there are areas where we're going to get trough meets crest. So you can see we're using the yellow lines, where you'll see when I put them on, you can see, especially in the middle of those yellow lines, where the purple lines cross over on the orange lines of the wavefronts. I'm getting a trough meeting a crest. Now the yellow lines, the yellow hatched lines, basically show the positions where this will occur. And the result of that is that you're going to get diminished amplitude, destructive superpositioning. Now you can see if you follow the yellow line, you'll get 2 areas where you've got the purple hatched line crossing with an orange wavefront. This is a trough meeting a crest. And these carry on in between the constructive antinodal lines. Okay, so I hope that makes sense with respect to these two lining up, where we get standing waves which are generated between crest meeting crest and trough meeting trough, and then we get standing waves which are generated where we get crest meeting trough. So how does that look on a wave intensity graph? Well, what we'll notice is that we'll get a graph similar to this. The center point will be of highest intensity, literally because the energy which has been generated in the wave is all going to meet together at a single point. The further out we go, the intensity is going to decrease, literally because the waves have got further to travel, so it's going to lose some of the energy. And we get this fringing pattern which is generated. So let's have another look at how this works with respect to light. Now, in order to do this with light, Thomas Young used what was known as a double slit. And basically it's made up of a piece of glass which has got some black carbon paint painted on it. By taking a very fine needle and making a nice scratch, very fine scratch, and then another fine scratch, he produced two slits. Now generally, in order for this to work, you need to use monochromatic light. And monochromatic light is light of the same chroma or colour. So it's the same wavelength. So you've got a single wavelength of light which has been generated. Best way to do this is using a laser. Now what happens is, because light is quite narrow, the slits have the effect of producing 2 point sources of light that come through the black paper. Nowadays we call these pieces of black paper, they're very, very fine. We actually call them diffraction gratings. We won't really be studying that in this unit, but literally this is an early form of diffraction grating. But the principle behind it is it produces 2 point sources. Now what then happens is these point sources can then interact as they pass through. And this is the evidence to show that light can work in the form of waves. Because what he experienced was we got antinodal and nodal patterns which are generated with light. We got it in the ripple tank with water, but he also got it with light. Now you can see here that as the light passes through, we get our antinodal lines and we get our nodal lines. And they come across as a banding pattern on the screen. Those banding patterns basically consist of fringe patterns of light, where we get a large one in the middle and then it gets gradually more diminished as we move out. The dark areas are basically areas of destructive superpositioning, where we basically get no light which is generated at all because it cancels out. So let's have a look at how this forms. So we've got our antinodes there, our nodes there, so let's look at how it forms. So here we've got our same diagram, we've got our screen in the white line, and we're going to shine our light. We're just going to look at that initial standing wave which is produced down the middle. So basically what happens if light travels in waves, it's generated from A to P in this format with the purple line. From B to P, you will notice it will go in the opposite direction. But because it's coherent light, you'll see that peak meets peak, trough meets trough. As the light moves through, it's going to interact. The result is, as it interacts at the same distance, we're always going to get peak meet peak, trough meet trough. At this point, we're always going to get a standing constructive wave which is generated. Now, as we go from further up the screen, we will notice further standing waves which are going to be generated. And as a result, on our screen, we are going to get these fringe patterns. Obviously, as I stated earlier, the dark areas in these fringe patterns are going to be the nodes, where we get this destructive patterning occurring. Well, I hope that sort of explains how wave interference patterns come about. Next video I'm going to look at is how we can use this to work out path difference, or use the idea of path difference to work out whether we're working on an antinode or a nodal point. So I hope you've enjoyed this video and it's made sense, and I look forward to you joining me again. Thanks for watching. Oh, by the way, one little aside, I've put another video on from PhET, which will also help explain what's going on. So join me again, and I look forward to seeing you. Thank you.